Okay, let's start the review session. And um, before I give the solution for the practice final exam, probably let's review some basic stuff we learned this semester. So first, we learned how to do operations on vectors and dot product, cross product, etc. And secondly, we learned how to parameterize geometric objects. For example, how to parameterize plane, lines, curves, surfaces, etc. How to write down the parametric equation and what is the domain for your parameter. And thirdly, we learn how to take partial derivatives. In second midterm, we did a lot calculation of this stuff, so I suppose you already know that. And then we give a high dimensional generalization for the min-max theorem or maximize or minimize some function. Of course, sometimes we introduce Lagrangian multiplier. But I should say, this method has its theoretical importance later in your study, or no matter optimization or physics or computer science. Okay, so sometimes I know sometimes when you do computation, you find out the Lagrangian multiplier is just redundant. Without it, you can also solve the problem, but I should say theoretically it has its importance. And then we talk about how to do double integral and triple integral. So those integrals are the basics of the later calculation, because here you don't have the orientation or stuff. All you have is, if you are in 2D, then you are integrate dx dy, in 3D dx dy dz. And of course, immediately we introduce some convenient coordinates, spherical, cylindrical coordinates. And when you do transformation between integrals in xyz coordinates and the curved coordinates, you will have some Jacobian. Okay, and then later we study how to generalize this integral of some solid domain to some embedded smaller objects. For example, embedded curves. From that, we have the line integrals. And by the physical property of the definition, you will have two kinds of. So first kind, second kind. Okay, then if you have embedded surface, then you have surface integral. First kind and the second kind as well. And some easy application is you can compute the area of some surfaces, okay, and some volume of some solid enclosed by surfaces. Okay, next we talk about the Green theorem, which gives you an alternative way to do calculation. Due to time, we are not able to cover in its full generality of the Stokes theorem and the divergence theorem. Okay, I should say here the operation on vectors. Later, we also learn some fancy stuff, curl, divergence, and what's that? And also for the vector field, we learn how to find the potential of some vector field. Yeah, that's most of the part we learn in this semester. And yeah, and basically what we learned in the notes is possibly to be on your final exam. Okay, next, let's talk about the problems in practice exam. First two questions, I think you are able to find the solutions either online or from the worksheet. So I will not talk about that. So first problem, then I will talk about the derivative problem first. So prove that. I should say here, although it's proof, but just calculation. Probably I should not say proof. Has a following form in the polar coordinate. Equals partial square r partial r square plus 1 over r partial f partial r plus 1 over r square partial square f partial theta square. Okay, next solution. There are a lot of methods to calculate, but I will choose the following one. So we noted that x is r cosine theta, y is r sine theta. And we noted that it's easy to take a derivative of xy with respect to r and theta instead of the derivative reversely, because otherwise you will have square root. It's not that convenient. So we would like to compute the easy partials first. So partial x partial r cosine theta, partial y partial r is sine theta, partial x partial theta is minus r sine theta, partial y partial theta is r cosine theta. Therefore, when we have f, we can talk about theta derivative. Okay, then what do you have? We can use the train rule. Partial f partial theta equals partial f partial x times partial x partial theta plus partial f partial y times partial y partial theta. You see here, we represent partial theta in terms of partial x and partial y, the advantage is the transformation we need is partial x partial theta and partial y partial theta, which is easier, you see, which is very clean, just a product, just a trigonometric or the product of some easy functions. Okay, and then we can, because we have no information on this, and we can keep it. So here you have partial x minus r sine theta plus partial y plus r cosine theta. Similarly, we can transform partial f partial r into partial x and partial f partial x and partial f partial y. Okay, then here you have fx cosine theta plus fy sine theta. This is first order information. So first order derivatives. Noted that the right hand side involve both first order and the second order. And eventually, if you want to compute the second order, you need to know first order. So the first order derivatives are unavoidable. Okay, next, look at your right hand side. You only have partial RR. So let me write partial R, and partial theta, partial theta. So you don't need to calculate the cross term, partial theta, partial R, because on the right-hand side, you don't have that. Therefore, in the following, we will compute this derivative. And here, we view the inside first order derivative as a function implicitly in R and theta. Here I say implicitly because you have some intermediate variable, x, y. Or probably I should say here, the strategy we do that is you have f depend on x, y, and then you depend on theta, r. Go this way. This is a diagram. Okay, now let's take the derivative. So first, when you take theta derivative of fx, remember you cannot take theta derivative of fx abstract because fx you can write down as a function of x and y. Therefore, you need to have one intermediate variable. Okay, so let's use product rule. Yeah, to make life easier. We first use product rule, and then the basic idea is decompose the whole complicated thing into small pieces. Plus fy times partial theta r cosine theta. Okay, now let's do easy part first. You see here, theta derivative of negative r sine theta and theta derivative r cosine theta are both easy. Yeah, we didn't do anything about the first one, so we keep it. Plus fx, and here you have negative r cosine theta plus partial theta fy r cosine theta plus fy minus r sine theta. Yeah. Okay, then let's deal with this guy. And this guy we use chain rule again. So partial x partial fx times partial x partial theta plus partial y fx partial y partial theta. This is the red part. And then you have negative r sine theta. And then you have fx negative r cosine theta plus partial theta. Okay, so here similarly you will have this one. Partial, you by chain rule, partial x fy partial x partial theta plus partial y fy partial y partial theta times r cosine theta plus fy negative r sine theta. Okay, then we plug in all we know. So fxx, you cannot simplify anymore because you don't know any information of f. And then partial x partial theta, this is negative r cosine theta. Sorry, negative r sine theta. And then you plus fxy r cosine theta. This is partial y partial theta times negative r sine theta. And plus fx negative r cosine theta plus here fxy partial x partial theta is negative r sine theta. And the partial yy r cosine theta times r cosine theta. Okay, let's do distribution first. So fxx r squared sine theta squared minus fxy r squared cosine theta sine theta minus rfx cosine theta minus sorry, here you have r cosine theta negative r sine theta. Yes, you have actual. So be very, very careful because right hand side we don't have fxy. So whenever you have xy, you should be very careful about the sign. So here you have r squared cosine theta sine theta and plus fyy r squared cosine theta squared. Okay, here I omit one term. So here you should have minus r sine theta. Just here. Don't forget anything. Otherwise, you cannot derive the correct answer. Okay, and if you want simplified, you could minus 2fxy r squared cosine sine plus fyy r squared cosine squared minus fx r cosine minus fy r sine. So this is partial theta. Now let's take a derivative of this one. So this is partial r, partial f, partial r. And we recall what is partial f, partial r. This is fx times cosine theta plus fy times sine theta. Then if you use product rule, you would only have this because r derivative of theta, cosine theta or sine theta is 0. Okay, and then you plug in what is your fx. This is what is partial r. Use the chain rule. Again, partial x fx times partial x partial r plus partial y times fy partial y fy times partial y partial r cosine theta, and plus here same thing, partial x fy dot partial x partial r plus partial y fy partial y partial r. Oh, sorry, here is x times sine theta. Okay, then you have fxx cosine theta plus fxy sine theta times cosine theta, and plus fxy sine theta, cosine theta, plus fyy sine theta times sine. Or if you want to simplify it, you can do one more step. That is fxx cosine square plus 2fxy sine cosine plus fyy sine square. Okay, now let's look at what is your right hand side. It's partial r partial theta divided by 1 over r squared, and 1 over r partial f partial r. So let's compute. Right hand side equals partial f squared partial r squared plus 1 over r partial r plus 1 over r squared partial square f partial theta square. And this is so let's collect terms. Fx x cosine square plus 2fxy sine theta cosine theta plus fyy sine square. Okay, then you have, this is second order terms, and then first order term you have recall what is partial f partial r. It's here. So what do you have? So here you have plus 1 over r fx cosine theta plus 1 over r fy sine theta. Okay, then next you have 1 over r squared partial square f partial theta square. So recall previously we computed, the answer is here. So you plug in, what do you have? You have you have fxx r square sine square minus 2fxy r square sine square cosine square sine times cosine plus fyy r square cosine square minus fx r cosine theta minus fy r sine theta. Okay, now let's combine terms. So first look at the first order term. So this cancel out with this, because here you have 1 over r square and divide r, so you have 1 over r totally, and then similarly this cancel out with this, and then for the cross terms this cancel out with this. So finally, what do you have? You have fxx cosine square plus sine square plus fyy cosine square plus sine square, which is fxx plus fyy. Yeah, I think the difficulty is the competition is difficult, but I think most importantly, if you make mistake in this problem, either by some algebraic calculation or you are a little bit confused about the concept train rule, how to use train rule, which are your intermediate variables, which are the free variables. Sometimes they are mixed together, but you need to be very clear what you should do, which derivative you should do, and which train rule you should use. So this is the point of this problem. We want you to do some practice of the train rule. So how to make the concept more clear. Okay, next, let's talk about the flux problem. So suppose, so S is the surface given by the quarter of the right circular cylinder, center on the z-axis of radius 2 and height 4, which lies in the first octant, and the field F is given by xi or x00, and compute the flux cross S or F, and the S is the orientation of S is outward. Outwards. Okay, so let's first draw the picture. So suppose this is your so radius is 2 and the height is 4. Okay, you can imagine. So if you don't buy it, let's make the picture a little bit better. Okay, now before we do calculation, let's draw the normal direction. So we divided. So you see, so the cylinder has 5 pieces of boundaries. So the one lie on the xz plane is let's call it S1. The one lie on YZ plane, let's call it S2. The one on XY plane, let's call it S3. And then parallel to S3, you have S4. And then you have some curved one, circular one, which we call S5. Okay, and then correspondingly, you have a normal direction for each piece. So for example, for S1, you will have N1. And for S2, you will have N2. S4, you have N4. S5, you have N5. S3, you have N3. Eventually, because we are calculating second kind surface integral, so we need to have explicit numerical data of the unit normal direction. Actually here, except S5, it's very easy to calculate the others. For example, N1, you can just write down, this is, because you see it's parallel, N1 is parallel to Y and opposite to the negative Y direction. Therefore, it's 0, -1, 0. And N2, similarly, is given by -1, 0, 0. N3 is given by 0, 0, -1. N4 is given by 0, 0, 1. N5, you need to do a little bit of calculation. We'll leave it later. Because it depends on your parameterization, so we would like to have the parameterization first, and then give the orientation point-wisely, which is easier. Okay, now let's decompose the whole. Let me denote this as I. Then is to see the whole integral I is a summation of S1, S2, S3, S5, sorry, S4, S5. Okay, and then we can calculate one by one. So first, some are very easy because of the special form of the surface and the vector field. So for S1, what do you have? So S1 F dot ds. Remember, this is F dot N1 ds. And since your F is x0, 0, your N1 is 0, -1, 0. If you do dot product, it's 0. And similarly, S3, because S3 is the bottom, so you will have the same thing, S3 x0, 0 dot 0, 0, -1 ds, which is 0. And then also S4, you will have it's 0. Okay, and then for S5, sorry, S2, we have the following. S2F dot N2 ds, and recall N2 is -1, 0, 0 ds. So here you should have -x ds. It seems like it's not there, but noted that S2 has x coordinate 0. Therefore, when you plug in, no matter what parameterization you have, so because the points of S2 can be write down as, no matter what parameterization you have, for easiest, you can take this as your parameterization, and then you plug in x is 0. Therefore, you are integrating 0. Okay, then what does that mean? That means your I gets contribution only from S5. So what is S5? This is F dot M5 ds. Okay, now we should give the surface a parameterization to calculate this one. So parameterize by cylindrical coordinates. So gamma Z. See, because R is 2 already fixed. And more explicitly, X is 2 cosine, Y is 2 sine, Z is Z. And also, theta is from 0 to pi over 2. Z is from 0 to 4 by the condition. Okay, next, let's compute the partial theta, partial R. So this is negative 2 sine, 2 cosine, 0. Partial R, partial theta, this is, partial theta, partial Z, just 0, 0, 1. So if we do cross product, you will have ijk minus 2 sine, 2 cosine, 0, 0, 0, 1. So if you compute, you will have I 2 cosine theta, 2 sine plus j 2 sine theta. That's it. You don't have k component. Or you have 2 cosine theta, 2 sine theta, 0. And you can compute the norm if you want. Just square root 2 cosine theta square plus 2 sine theta square, which is 2. Okay, then we need to decide what is n phi. This is crucial. From picture, you know, it point outwards, and candidate we have is the normalized, the unit normal vector here. So if you compute this guy, you have cosine theta, sine theta, 0. But we need to check the direction, because we already mentioned that for parameterized surface, the order of your parameter matters if you use this formula to decide the unit normal vector. If you change the order of theta or z, then you have minus sign. So in principle, it's not canonical. We don't know if it matches with the outwards orientation. We need to check. So noted that, so cosine theta, sine theta 0. For example, we check here at this point, and we know that the direction given by, so let's call this quantity. Red one, just this quantity. Points go this way. You check point, because at checkpoint, so let's at 1, 0, 0, so theta is 0, z is 0, so partial r partial theta cross partial r partial z divided by whatever here, and this is 1, 0, 0. So that means it points outwards from the picture, right? You have this. Okay, therefore this, you only need to check a point, and here at this point it points outwards. Therefore n phi is given by the one you derived from the parameterization. So So we spend a lot of time to check the sign. If you don't care about the sign, then you already know that. But the key point here is the sign is very, very important. Otherwise, you just mess everything up. You do a long calculation, but then finally you get the right answer. Okay, now we turn back to the calculation. S5 F D S, and recall the formula we have is S5 dot, so it's x00 dot m5. So let me write one more step. F dot m5 ds. So here f is x00, so it's cosine theta 00 dot cosine sine. Oh, sorry. Here 2 cosine because x is 2 cosine theta. 0 cosine sine 0 and ds. I know we have another formula for that. You can use that formula. Just let me mention. I know you have this formula, d theta dz, blah blah. But I don't want to use that directly because I want to track the sine. So you can do that. It's equivalent. So here you have 2 cosine square s phi ds. Now you plug in. So this will be, we use the first surface integral of first kind. So theta is from 0 to pi over 2, and z is from 0 to 4, 2 cosine square, and then you have this Jacobian kind of stuff, dz d theta. And this is 2, so we already computed. So here finally you have 0 pi over 2, 0, 4, 4 cosine square theta d theta, and 0 pi over 2. If you integrate z, you just get 4. So you have 16 cosine square and d theta. And then you have use the triangle formula d theta. So you have 8 times 8 theta plus 4 sine 2 theta pi over 2, 0. So finally you have 4 pi. Okay, next. So I should say when you have this kind of stuff, because whenever you are computing flux, you will have a closed surface. Then it's highly possible that you will have several pieces. So don't be frustrated or don't be discouraged. Although you have several surfaces, each one is very easy. So you just be patient and sit down, write down your answer. You have enough time, to be honest. So take your time and compute one by one. Even if you make one small mistake when you're computing one piece, it's okay. We will give you partial credits for the others if you do that right. Okay, next let's talk about the actual credit problem. Actually, this problem is a little bit easier than the previous one. So suppose you had the vector fields given by this, and then the question 1, so compute the line integral along C1. So what is C1? C1 is unit circle oriented counterclockwise. So let's compute this. Actually, we computed that before, but this problem is easy, but we would like to discuss in detail. So parameterize it. We use x is cosine theta, y is sine theta. Theta is from 0 to 2 pi. And then, so what is gamma prime? Gamma prime is just a theta derivative, so negative sine theta, cosine theta. So what do you have when you're computing this one? By the formula, the theta, theta is from 0 to 2 pi. Okay, now what do you have? Here, f is negative, y is sine. So in the denominator, you have x squared plus y squared. So it's cosine squared plus sine squared. And then the next one is cosine divided by cosine squared plus sine squared. Okay, and dot product, negative sine, cosine, integrating with respect to theta. Okay, then what do you have? Then you have, here do calculation, you find you are integrating 1. So it's 2 pi. Okay, so second problem is, suppose you have ellipse x squared plus 2y squared equals 4, and also oriented counterclockwise. So let's draw a picture roughly. So the x-intercept is negative 2 and 2, and the y is negative square root 2, positive square root 2. Okay. So method 1. You can use x is, let's see, 2 cosine theta, y is square root 2 sine theta. Use this parameterization, you can solve, you can compute. But then the problem is you might have some kind of 1 over 1 plus x squared, which is arctangent stuff you need to take care of. It's doable in Calc 1, but probably you forget how to do that. Okay, and then method 2 we learned before. We want to make this curve easier for computation. And by Green's theorem, we know that you can deform this curve to the green one. C1, C2. Okay, then you have integration along C1 equals C2. That's what we discussed last time. And what is C2? C2 is x squared plus y squared equals 1. And counterclockwise oriented. Okay, and then we compute from equation 1, so it's 2 pi. It's easier. Okay, now let's look at the vector field a little bit. We are done with the problem, so I would like to see something more. So here you will have what's your field? Negative y. X squared plus y squared. And note that this field is not defined at the origin. And same time, for the other points, all the other points is well defined. And also, you can compute the curl, which is 0, for any other points. Okay, then you will have this kind of stuff. For example, if you have a point here and another point here connected by a curve like this, and then you can do small deformation of your curve. So for example, if you want to compute the line integral, this is not closed anymore. You might have different answer than 2 pi. But then you can deform it a little bit. For example, you can deform it to this. I don't know if it's easy to compute, but you have a lot of choice. But the problem is you cannot deform to this one, because if you do deformation, you have to cross the red part. Okay, so that means these two curves are not same. You cannot apply Green's theorem. Yeah, that's it. So that's all I want to see. And this first remark. So someone might ask how to calculate this one. Then you just, okay, so suppose you have this piece. If someone forces you to calculate this using this line, let's call this as C2, this as C1, then what should you do? Although C1 and C2 are not same, but you see C1 with counterclockwise orientation, and here C2 is clockwise, so we need to give it a minus sign to reverse its integral, reverse its orientation. FDR. Sorry, so let's more careful. Let's write more careful. FDR minus integral C2 FDR. What it is, that gives you just this curve, and then you can deform it to this one, a unit circle. So this is, because then you can have Green's theorem for this part. So this is integration of red one, so let's call C3. And I would like to give it a small circle here, means it's a closed curve, FDR. And this one we all know is 2 pi. Okay, so that means if you really want to compute C1 by the detour, then you need to give an extra 2 pi extra circle here. This is different from the previous case. Okay, and remark 2, suppose your domain is given by cutting one line. So you don't want this line, and your domain is the remaining part. And if your curve falls in this side, if your curve just in this domain, then you can deform it as soon as it's in this domain. It's independent of path, or in other words, you can compute let's call this domain as the theta. Compute the potential function of f on d theta. You can do that, and actually you can use a method we introduced before to calculate this. Okay, I will not spend too much time on this. Okay. And so the key idea of those fancy theorems is that if you know that and sometimes it applies, then your computation will be super easier, just like this one. If you use Green theorem, method 2, just 2 pi. And if you don't know that, you can still do that, do the calculation, but you need to be very powerful, very persistent. You can try the first method here. It involves arctangent stuff. It's a good exercise. Okay, I will stop here, and good luck. If you have questions, please email me, and we can make an appointment if you want.